Hello, I'm Duncan Neill, a postgraduate student at the University of Bath. And yeah, my talk's on resonant shattering flares and multimessenger probes of nuclear symmetry. So I'll just start by talking about what we think ISFs might be. So you might know that SGRBs are short gamma ray bursts. SGRBs are produced by neutron star mergers and probably also black hole neutron star mergers. But also before small percentage of SGRBs, we see these short precursor flares, which are these. I've shown you a couple of examples on this slide. These smaller flares that occur before the main SGRB peak, and it's not quite clear what these smaller peaks are. But the theory we're working with is that they are resonant shattering flares. So a resonant shattering flare is where during the orbit of two neutron stars, during the late stage in-spiral, the tidal field of one of the neutron stars resonantly excites the oscillation modes within the other star. And by exciting those modes, they may eventually grow to amplitudes where they begin to strain the neutron star crust past its elastic limit. At that point, the crust may fracture, releasing seismic waves into the neutron star crust, which can then, and if this happens multiple times, these seismic waves will end up at higher frequencies where they can couple to the neutron star's magnetic field. This will lead to the emission of a fireball, and if you get multiple fireballs while the mode's in resonance, then they can collide to produce a non-thermal flare, which is what we think these precursor flares might be. Throughout in the past couple of talks, we've heard about, say, the F mode, the fundamental mode. In this case, the mode we think might be getting resonantly excited is the crust-core interface mode, which is at a lower frequency than the fundamental mode, and so is able to be resonantly excited during the in-spiral rather than during the post-merger phase or anything like that. And so this is the mode we think that might be getting resonantly excited to cause these flares. And importantly, this mode is very dependent on properties of the neutron star crust, and I'll get back to that later. But for now, to test whether resonant shattering flares could be these precursor flares, we'll do a quick plausibility test. So using a model for the non-thermal emission from these colliding fireball shells, we've checked how long and how bright these flares might be. So we find that the duration of these flares is about the length of the resonance, while the time span the mode's in resonance, which is about 0.1 seconds, and that the luminosity is around 10 to the 48 ergs per second, mostly in gamma rays, although there's some dependence on the neutron star's magnetic field, as that determines how rapidly energy can be extracted from seismic waves into these fireballs and so into flares. And so so this plot shows a few different examples of what these flares might look like. And so if we add this to a couple of real SGRB detections, it will look something like this. So the top plot here is 170817, and so which is a nearby merger, and the bottom plot is a slightly further away GRB. So the flare appears. So we see a lower photon count, and you can see that we get this small peak sometime before, a few seconds before the merger, which is visible up to maybe a couple of hundred megaparsec. So you can imagine something between these two distances shown here might look quite similar to those precursor flares I showed on the earlier slide. So there's a good chance that these ISFs could produce something that looks like these precursor flares. But the question is, why am I talking about these ISFs in a gravitational wave conference? Well, what we can do is, if we have both the gravitational wave signal and this ISF, then what we can do is we can use the timing of the ISF to get the frequency, to get the gravitational wave frequency at the time of the resonant shattering flare. And that will inform us of the frequency at which the mode which caused this resonant shattering flare was excited. And because that frequency, as I mentioned earlier, we're looking at the I mode, the interface mode, this mode is very dependent on the neutral side crust. So if we can infer its frequency, we can also learn about the composition of the neutral side crust. And this is done through the gravitational wave frequency. So from the gravitational wave frequency, we learn about the mode frequency. And from the mode frequency, we learn about the composition of the neutral star crust. So this is what we've been doing. We've been looking at what we can learn from these multi-messenger detections, and in order to do that, we've had to construct models of the neutron star composition and equation of state. So you might know that from gravitational wave detections, we can learn about tidal formability, which constrains the neutron star core. But we don't learn much about the neutron star crust from tidal formability. So what we do in our model is we parameterize the neutron star crust with the, we parameterize a nuclear model with the nuclear symmetry energy parameters, and then use that model to generate neutron star crusts, which we then attach to neutron star cores informed by the tidal formability. These nuclear symmetry energy parameters, which we parameterize the crust with, are important parts of fundamental nuclear physics, which basically determine the difference in binding energy between symmetric nuclear matter and pure neutron matter. And so they're very important for all sorts of nuclear matter. And so on the right here, I've just shown various past constraints that nuclear physicists have tried to place on these parameters using various particle collider experiments. And so with neutron star compositions and equations of state parameterized with these parameters, we then perform Bayesian analysis to try and look at what we might learn from an ISF detection. So we have priors informed by causality of the equation of state, making sure that, say, the speed of light is obeyed. And we also inform them from NICE's mass radius constraints from pulsars and from G-78's tidal formability. And this mainly constrains the core parameters, the two on the rightmost two parameters, and doesn't really constrain the leftmost parameters, which are more to do with the neutron star crust. So what we do is with these priors, we inject a precursor flare at a randomly chosen frequency. There's no real detection, so we just pretend we have one to see what we might learn from something like this. And then we perform MCMC to perform Bayesian analysis and get a posterior on these parameters. And you can see that the posterior in red is basically unchanged for the core parameters on the right, which is what we expect. And for the crust parameters on the left, we actually learn quite a lot, in particular on the two I've highlighted here, the combined plot of the first two symmetry parameters, and on the second, and on marginalized second symmetry parameter, which are the ones I plotted on the previous slide. So we learn quite a lot about these important parameters for the neutron star crust. And if we add this back into the previous slide with all those nuclear physics constraints, we can see that the RSF constraint here in black is fairly competitive with these constraints from particle collider experiments. And it's important to note here that this constraint we get is actually very simple to get once we get these multi-messenger detections. All you need is to have an RSF be observed and have a gravitational wave signal at the same time. You don't need any details of the RSF, and the only thing you need to know about the gravitational wave signal is the frequency at the time of the RSF. And so these are fairly free, we get these for free pretty much from these multi-messenger observations, and they're as strong as constraints from these incredibly expensive time intensive particle collider experiments. And so at the bottom here, I've just shown that also from gravitational waves, we get the tidal formability, which constrains the neutron star core, and we also get the RSF timing, which constrains the neutron star crust. And these two are pretty much completely complementary. The tidal formability barely tells us anything about the crust, and the ISFs tell us barely anything about the core. And so putting them together, we can learn about the entire neutron star composition and equation of state. And so in conclusion, we've basically learned that ISFs could be visible during neutron star mergers and possibly also during black hole neutron star mergers. I haven't mentioned that, but another advantage of ISFs is that unlike other EM counterparts, they're not really affected by whether it's a black hole or neutron star resonantly exciting the neutron star. So that's another advantage. We've also learned that through multimessenger detection of these events, both in EM and gravitational waves, we can constrain the crystal interface mode's frequency and therefore the composition of neutron crust, which in turn constrains these fundamental parameters of nuclear physics. And these constraints are competitive with terrestrial collider experiments, which there's been many of because nuclear physics is very interesting constraining these parameters. So yeah, thank you for listening.
Thanks very much, Duncan. So while I wait to see if anybody else has any questions, one question I had is you say that these observations can be competitive with experiments from major particle physics colliders. How many multi-messenger observations would we need to have in order to be better than what you can do at the moment with particle physics, or is that just not something that you can reasonably do just with observation?
So we've not looked into that yet, but one thing you could do is because the neutron star mass affects the frequency at which the mode oscillates. If you got ISFs from neutron stars with different masses, you might be able to get the constraints much thinner, but I'm not sure how many measurements you would need exactly.
Okay, well, thanks very much. That